So welcome everyone to today's seminar. Today we have a pleasure to have Glenn van de Ven's talk. He obtained his bachelor's, master's, and PhD in astronomy at the Leiden University in the Netherlands. He was then a postdoc and then a Hubble Fellow at the Institute for Advanced Studies in Princeton in the US. And then he held staff positions in Heidelberg in Garching. And finally, he's now a full professor at the University of Vienna in Austria. His research interests revolve around uncovering the mass distribution and formation history of galaxies and globular clusters through population dynamics of their stars. He is the head of the research group Dynamics of Stellar Systems in Vienna. Thank you so much, Glenn, for accepting our invitation. You may start when you're ready.
Yeah, just to check, can you hear me clearly? Is it okay?
Clearly, yes.
Okay, great. Share the screen. And just to check, yes, you can see my screen.
Yes.
Yes.
Okay, great. Okay, thanks a lot for the invitation and for the introduction. It's a while giving a colloquium online, but let's try. So if there are questions, then please interrupt me if that's feasible, but otherwise towards the end of the talk. So I hope to try to give you an insight today of what we are doing here in the research group in Vienna, but also with a lot of collaborations across the world. And so let me start with give you a little bit introduction on what is the setting. So, and I'm trying to, let me see if I, 1 second to just annoy this annoying, yes, good. So the setting is to really try to understand galaxy evolution, and especially what we're after is two sides of galaxy evolution is their mass distribution. How do galaxies evolve in time concerning their mass? But also the other side is really how do they assembly? Yeah, so how is can we really follow the hierarchical buildup of galaxies? And so one way to do this is to look at galaxies at higher redshift. And so especially with the James Webb Space Telescope, this is of course fantastic to get better and better images and also spectra of galaxies at higher and higher redshift. So this is really complementary to what we are doing. And the main reason, the reason for to look for complementary approach is that this looking back directly in time by observing higher redshift, you can only do for populations of galaxies. So you cannot do this for individual galaxies. You cannot link in individual galaxy across time. So you're principally limited to do this in a statistical way. And so a complementary way is to look at nearby galaxies and really look at signatures for their past evolution. And like I think all of you have seen these beautiful, and this is just one example on the screen, deep images where you see shells, streams, and these are all markers, signatures of past events, of mergers in this particular case, satellite mergers. And this is really like really giving you a picture, but it still gives you a picture only of, relatively speaking, only of the last few gigayears, because these features will very quickly disappear or become diffuse. And so one way to do that is to, what we want to do is try to see, aside from these photometric features, which look back like a gigayear or so, can we look in the memory of the stars that got accreted in their chemical and their population, hence also the talk title, and really recover also features that happened much longer than 1 gig a year. Go for a single galaxy and then look back in time. And so this sounds maybe completely hopeless because, of course, these accretion events, let's say it happened 10 gig years ago, all these stars are now mixed. Yeah, so is it at all feasible to think from the smooth distribution, like in this particular galaxy? This is a lenticular galaxy in the Fornax cluster. It's completely smooth light distribution. So is there any hope that we can get information about this past? And so I hope to convince you by the end of the talk, the answer is yes. And the reason is twofold, because of the fantastic new data that we're able to collect, plus methodology development. And so the typical data that we are using for galaxies is so-called integral field spectroscopy. And here, what is shown integral field spectroscopy. I don't think I can use my mouse, actually. Okay, good. I will try to just talk through. So in the bottom left corner, you see an illustration of the MUSE integral field unit on the Very Large Telescope. And in principle, what these integral field units do, they map galaxies in wavelength. So you get in principle a spectrum at each position on the sky where you point the MUSE. So you see here with the purple squares, you see the field of view of MUSE on this particular galaxy in the Fornax cluster. So there are 3 pointings here, and I will show you a couple of times data that you can extract from this IFU. And so there are some numbers. So this particular galaxy, which will be the main player of the talk today, it's called NGC 1380 or FCC 167. It has a stellar mass around 10 to the 11, and it's quite large with an effective radius of 6 kiloparsec, and it's really at a distance of beyond 20 megaparsec. Okay, so I split the talk into 3 different parts. So the first part is really focused on what can we learn from the stars. And then the second part will be what can we learn from the motions of the stars or the dynamics. And the third part is really combining the two. And so here are, again, here's already some data. So to the top again is the same picture with the field of view of this MUSE instrument. And to the bottom, you see two maps of data that you extract from this. So the contours are the same as the pointings. And on the left, you have the light-weighted average age of the stars in this galaxy. And you see that all stars are old, but there is a variation from being 12 years to 13.5 gig years old stars. And then on the right bottom, you see the plot is the metallicity, a metallicity measurement of the stars. And there you see more variation, but what's apparent here is that this lenticular galaxy, there is more metal rich in the disk region than in the outer part. Yeah, so this is the kind of like high quality data that you can extract with this instrument. And you see the bins in the outer part are larger, but there we're already at 3-4 effective radios, so very far out in the galaxy. In the central part, you have thousands of different data points. So the quality of the data of these spectra is actually so good that you can go beyond like an age and metallicity. And for example, you can also extract on the left bottom an alpha element, so in this case magnesium over iron map. And then on the right is something that is relatively new. This is really a measure of the IMF, stellar IMF, or at least a diagnostic. So what is shown here is really the ratio of dwarf stars to giant stars. And so the reason that this works is because dwarf stars have a certain very low level, on the percent level, features in the spectra, yes, that are different from giant stars. So the giant stars, we of course are dominating in the light. The dwarf stars are dominating in the mass, but even in the light, like with this quality of data, you can measure the contribution of the dwarf stars. And so what you get then is what you see there is actually this is referring to a slope in the so-called IMF, because the slope of the IMF is the ratio between the low mass stars and the high mass stars. And what you see here is that this IMF is varying across the galaxy. Yes, so there's been long discussions whether the IMF is universal, like a Milky Way-like IMF. So that has already been shown that that's not the case. So the IMF globally varies between galaxies, and actually, if you are able to map it out within a galaxy, also it is changing. Yeah, so towards the center of this galaxy, it is more dominated by dwarf stars. Yeah, so it's also sometimes called bottom-heavy IMF. While if you go more to the outer parts of the galaxy, it actually becomes more and more closer to the Milky Way-like IMF. Yes, so it has the dwarf to giant ratio is closer to what is in the Milky Way. And so having all this information from the stars, the question is, what can we then learn from of the galaxy itself? And I will just give you one example that is being applied to date, but is still challenging. But what I show you here is the development from people also here working in a group based on simulations. And just to see the concept, so what is shown here is from an eagle simulations is on the bottom. On the left, on the top, you see a simulated galaxy, a massive simulated galaxy like the one that we saw the data from. And in the simulations, you of course have the advantage that you can really identify which stars were born inside of the host galaxy and which stars were born outside of the host galaxy and satellite galaxies and got accreted. And this is what you see here. So it is really in situ born stars, ex situ accreted stars. And because of a massive galaxy, we do expect that there's a lot of mergers, minor mergers, that bring in stars. And the stars will be mostly deposited in the outer parts. So that's what you see on the top left. So there are no surprises. What you see then on the bottom left is actually the age and metallicity distribution of all the stars. And you see all kind of features in there. Yes, and these features are actually related with the past of these stars. And so what you can do, you can then split up from the simulation, ask like which stars were accreted, yes, and how would those accreted stars look like in this age metallicity diagram. If you see that on the right, for example, there's a 1% contribution in total in mass in stars from satellite galaxies, which are very dwarf-like, so 10 to the 6 to 10 to the 9th stellar mass. And you see that they occupy a different region in the age metallicity diagram than if you go to the higher mass satellites. Yes, and this is the feature, the difference in age metallicity of accreted stars with respect to in situ that we want to exploit to understand how many and what kind of mergers did happen. And you see, of course, there is a different feature, but it is highly overlapping. Yes, so this is not trivial, completely trivial to do. And the way it's done is, again, we use very, very high quality spectra. And from these high quality spectra, we not just measure a single age and metallicity, but we actually measure the full age and metallicity distribution. And then from this full age and metallicity distribution, there we can then model, yes, apply a model and extract like which stars are likely in situ, which stars are accreted. And the results, like if people are interested, there's a paper, but also more happy to talk about it. In the end, what you can show, so just to recap, this is a simulated galaxy. What we do, we make mock data out of it. So we make like Muse, like IFU mock data out of it. We get spectra, we collapse the spectra, we fit stellar population models to it, and these stellar population models then give us the age metallicity distribution, and then we ask which part of the age metallicity distribution is in situ and which is accreted. And if you do that, you can actually show quite convincingly that this allows you in a statistical way to really find back the how many satellites were accreted and what mass of satellites. So what you see here is on the bottom, the axis, you see the mass of the accreted satellites, and on the vertical axis, you see the number of the accreted satellites above a certain mass. Yeah, so this is a kind of satellite mass function. And then what in red is what is the true distribution, yes, which we directly measure from, which you can directly take from the simulations. Yes, you just go back in time with snapshots and you just count and measure the number of accreted satellites. And then the yellow-orange part is what we get from making a spectra out of it, extracting the age metallicity distribution, and then trying to differentiate in situ from ex situ stars. And you see that this works really well. Most robustly, we get also the slope of the satellite mass function out. So the reason this works, the reason behind it is actually very simple, is that if you have stars that are born in a lower mass system, they're typically less chemically enriched. So they will be typically more metal poor than if they're born in a more massive system. And this is the main driver why you're able to distinguish stars that were accreted in low mass systems from stars that were born in situ and metal enriched. And so this method has been applied now to a few galaxies and shown that indeed you can extract the ex situ information, but we are further developing it because it turns out to be that doing this with realistic simulations is still different from applying it to real data. But this is an ingredient, one side that we have. So this is an example from how you can really use the stellar populations to find out what was, in this case, the satellite merger history for this galaxy. And then the other side is what we do with stellar dynamics. And so here you use actually the motions of the stars. So here again, the same galaxy, and on the bottom now, instead of maps on stellar population properties, you get the motions of the stars. So the top left panel is really the mean velocity of stars. So blue means rotating towards us, red away from us. So you see that this lenticular galaxy has quite strong rotation, which you expect because it has a disk. And then on the top right, you see the velocity dispersion, which is highest in the center. Yes, and then goes down. And because of the high quality of data, you can also measure so-called deviations from a Gaussian distribution. Yes, so the bottom left and right are so-called Gauss-Hermite moments. These indicate a kind of skewness and kurtosis. Yes, and we will see later that these higher order moments are really important to extract the mass distribution. So this is the quality of data on the kinematics then, and what we built. So what our group has been developing actually already now almost 20 years is this, 15 years, is this so-called Schwarzschild or superposition technique. And so here is one slide that gives you basics on how it works. So you observe a galaxy. Yes, for example, and you get this IFU kinematics or integral field spectroscopy kinematics. So here's an example of an elliptical galaxy viewed almost edge-on, and there is the stellar velocity field. So this is similar as here, but with an older instrument, so the data is less good quality. But you see that even though the light distribution, it looks a very boring elliptical galaxy, in its stellar motion, it already shows you that something exciting happens, because in the disk plane, there is the rotation of the stars is on the right, that they go away from us, redshifted. While if you go to the thicker, like above the disk plane, yes, then suddenly the stars rotate the other way around. So this is nothing else than you have two counter-rotating stellar disks. Yes, and we show this example because this really illustrates well like what you can get out of this orbit position technique. So you would ask, okay, this is a very special case. No, there are actually many galaxies that show stars that are counter-rotating. Yeah, so this is not exceptional. What is exceptional here is that it's almost 50% in the thin stellar disk and the thicker stellar disk. Even those elliptical galaxies, these are kind of like thick disk, rotating, counter-rotating thick disk. So what we do then is, with the Schwarzschild technique, is that from the light distribution, we deproject and we get a measure of the mass distribution in stars. Yes, to get the mass distribution in stars, we need to deproject. So there is an inclination, viewing angle, that's a free parameter. And then we need to convert from light to mass. So there's a stellar mass parameter. So once we have the stellar mass, yes, then we can add dark mass. Yes, so we can add a black hole in the center, we can add a dark matter and or a dark matter halo. Once we have the total mass distribution, you can convert that with Poisson's equation to gravitational potential. And once you have the gravitational potential, you can calculate orbits in that gravitational potential. And that is what we did here. So what's shown here in this plot is, on the x-axis is the radius from the center outside. And then on the y-axis is a measure of the angular momentum of the orbit. So every point in there, like every grid point, is a single orbit. So we calculate in that gravitational potential, we typically calculate from 10,000 to 100,000 orbits. Yes, most of those orbits get zero weight, means black here. Yes, because they're not helpful in explaining the observations, in explaining the light and the motions of the stars. But some orbits get a lot of weight. And so here there are 3 orbits that I pick out. So the white means more orbital weight. So those orbits are liked by the model because they explain the observations. And so it's not completely surprising. So this is a small movie, yes. So if you take, for example, the green star there, that's a so-called bulge-like star. So that has very low angular momentum. And you see it describes, it's jumping up and down on the edge-on view on the top and the face-on view. So this is a random orbit, yes, or a bulge-like or radial orbit. But if you go to the red orbit, you see that it's staying more in the disk plane. And if you do the face-on view, it's not perfectly circled, but it is not far away from a circular orbit. And the blue one is identical or similar, but it's counter-rotating. Yeah, so this is how we build these models. So it's literally, you calculate orbits and you find out these orbits, they represent stars in your galaxy, and the weighting determines how well they help in describing this. And so you might be wondering, but you calculate 10,000 to 100,000 orbits, how many get weight? So typically a few percent, so a few thousand orbits get weight. And yes, this is in principle a degenerate problem, yes. But it turns out to be that if you're asking questions like, I want to measure a black hole or dark matter halo, or I want to know so-called velocity anisotropy, it actually, it converges really well. Yes, and you don't have to do a lot of smoothing in the problem. Yes, so the method itself is very robust. Of course, if you want to start recovering like very tiny details in the structure of your galaxy, then you have to be more careful, and you have to ask the question, what kind of smoothing do I apply? So good. So now exactly this technique, this orbit-based modeling, we also applied to this galaxy that is the player of today. And now what you see here on the top, on the row that is shown there, is again the same kinematic data. Yes, so but now also the surface brightness, so the light distribution, surface brightness on the left, then the mean velocity of the stars, then the dispersion of the stars, and these higher order moments. This is the data. Yes, and then the next row is the best fit orbit-based or Schwarzschild model. And you see that this orbit-based model is capable of extremely well fitting the details in the data. And then you can also look at the residuals. So the residuals are not completely flat zero, as they shouldn't, because in the data there are also non-triaxial features, there are asymmetries which the model by construction will not capture because it's an equilibrium triaxial model. Yes, so it should not capture all features, and these features itself that are left on the bottom, like especially in the kinematics, are very interesting because they might tell us something about like deviations that could be caused by a merger, etc. Yes, that's a completely different line of research that we are starting to investigate. For the rest of the talk, we will focus on assuming only the symmetric part of the model. And so what you get out of this, as shown with the illustration before, again, is the same plot of the orbit distribution. And now it's the same axis, so it's the radius again from the center to the outskirts. And again, this circularity. So 0 means these random orbits or radial orbits. +1 means disk-like orbits, and -1 means counter-rotating orbits. And in this space, now white means no weight, and you see to the top the orbital weight in percentage. The darker the redder the color, the more orbit weight. So just on the bottom left, I showed an illustration from this model for 3 types of orbits. So the left one is this so-called hot orbits. This is these radial orbits, the jumping ones that you saw before. Then the cold orbits are the circular orbits. And then in between are, of course, orbits which are like thick disk-like orbits. And so if you then go back to the plot to the right, then you see that there's like a quite messy plot in the sense that it assigns weights all over the place, but it's actually not that messy because there are really clear white gaps in between. So you can actually separate the galaxy in different components in this space. And so that's what we did here with these lines at the moment. So you see the top line between 0.8 and 1 of the circularity. These are really what we call disk orbits, cold disk or thin disk orbits. And then you see the next line is the warm orbits and then the hot orbits. And then the central orbits are the so-called bulge orbits that we identified. So after you split your galaxy in these physical components, you can, of course, start investigating what is the shape, yes, of these components. And then it turns out to be, and I'm not sure, yes, so for example, you can draw the surface brightness profile, yes. And then you here is, for example, show along the major axis and then the surface brightness on the vertical part. And then in yellow is the bulge. And this is a typical Sirchik profile. Yeah, so it's somewhere Sirchik with, I think, NS3 or so, Sirchik index. And then the cold disk or the cold orbit disk, the warm orbit disk, and the bulge, yes, orbit, the inner halo orbits, they are actually all consistent with an exponential profile. So this already shows you if you only have photometry and you try to decompose this galaxy, you most likely would come to the conclusion it has a bulge and a single disk. But this disk actually is not a single disk, but this disk is actually made of a thin disk, a cold disk, a warm disk-like, and actually this inner halo. Yeah, so this is already a warning that if you do the more physical approach with these orbits, then you actually find that it's not always corresponding to the photometric decomposition. So you have to be really careful with interpreting the photometric decomposition. Okay, so this is a decomposition, and this is just to show next that we didn't do this only for one galaxy, yes, because some people say this is a very expensive, complicated method, and actually that is not completely true anymore. This is now a kind of like standard modeling technique, and here is just a summary graph by Julia, where on the axis is the mass of stellar mass of galaxies that have been modeled with the same technique. And then on the y-axis is the orbital fraction. So these cold orbits, warm orbits, hot orbits, and counter-rotating orbits. And then for different surveys. And these are all then binned together because you can read off, we don't do this for a few galaxies, but for 260 galaxies, 149 galaxies, 161 galaxies. So you really have this now for large samples of observed galaxies. And then you can also do the same procedure by making mock data and then observing it also for simulated galaxies. And so in the shade in the background, Julia did same orbit-based modeling also for 3,500 simulated galaxies. Yeah, so this is not anymore a technique that is for a handful of galaxies, but we claim, and I think we've shown that this can be done as a standard modeling technique now. I will come back. The code is actually publicly available, and but come back to the end to that. Okay, so that's nice, but what are we going to learn from this? Yeah, so we do all this effort. What are we going to learn from this? So one thing that we can do from the dynamics very well is measure mass, including dark mass. And so here's one example of this orbit-based technique to actually get the supermassive black hole measurement in a galaxy, which is called NGC 1336. And so what you see on the page here now is purely the data. This is also a showcase of how excellent data nowadays we have. So on the right side to start with is the large field of view. So on the top you see the velocity of the stars, and on the bottom you see the dispersion of the stars. On the right side is the zoom out, yes, large field of view of the galaxy. Then on the middle panel you get a zoom in to the center, so you see that there is rotation like around the, let's say the horizontal axis, but there's in the center rotation around the different axes. And then with Symphony, which is a near-infrared, you can even zoom in further to the center. That is the most left column. And you see that in the center that the rotation is even faster. And at the bottom, you see there's a peak in the dispersion. And this peak of the dispersion is really an indicator that there is a black hole. Yes, because the black hole will make the stars around it go faster, and this will increase the stellar dispersion. So the question is now, can we measure actually the black hole that is there? And the answer is, otherwise I would not show you, yes. But, and the big but is, it really depends on how you model this. And especially it depends on what you assume for the stellar mass to light ratio. Because this peak in the center, yes, can be, of course, because there's dark mass, like a black hole, but the peak in the center could also be there because there's a lot of dwarf stars. Yes, if you have a lot of dwarf stars, you have a lot of mass, but relatively little light. Yes, so you can also explain such a peak if you would put an enormous amount of low mass stars. And so the question now is, can we disentangle the two? And the answer is, because of the high quality of data, I showed you the stellar population before, we have a handle on this dwarf to giant ratio. So if we put that into the models, then actually you can show that you can measure the black hole and it has an effect. So what you see in the constant mass to light ratio, so the orange line is the black hole on the horizontal axis that you would get. So it's around 8 times 10 to the 7. If you would do the traditional approach where you assume you have a constant stellar mass to light ratio. Yeah, so this is more or less okay for like an approach, an approximation, but it's really an approximation. And if you have better data, you should allow the mass to light ratio to vary. So that's done in the blue one. That is a varying mass to light ratio, but a fixed Milky Way IMF. Yes, so this is a Milky Way like IMF. Then you get a slightly lower black hole mass. And then if you move to the left completely to the green one, then you allow also the IMF to vary. And then you see that the black hole gets even lower. Yes, so you went from above 8 to slightly above 4. So it's a factor 2 effect on the black hole mass. And the reason is because there are actually a dominance of dwarf stars in the center. So these dwarf stars can explain part of the mass concentration. And so this is one case where we really could apply this. And within the group, we're now also checking this for more galaxies, yes. You could say, who cares about the factor 2 on the black hole mass? But if all this happens to all the galaxies, it is a systematic effect, of course. So then I wanted to briefly, like a small intermezzo, because these are really recent results. There are also predicted black holes in globular clusters, so-called intermediate massive black holes. And these are really exciting because they could be the seeds, yes, of the supermassive black holes that we see now at high redshift. So one possible way to grow already very massive black holes as seen by the James Webb Space Telescope at very high redshift, so only 500 million years after the Big Bang. The only way seems to be if you already start with a seed black hole of a few thousand solar masses. Yes, and that you can grow very efficiently then to 10 to the 6, 10 to the 7 black hole mass. Yeah, but you have to start with 1,000, 10,000 solar masses seed black hole. So if these seed black holes, where are they formed? And one possible way to form them is in so-called globular cluster or protoglobular cluster. But if they formed in these protoglobular clusters, then the question is, did they survive to those globular clusters that didn't merge into the centers of galaxies? Would they also have black holes? So this is why people have been really trying to find out, are there black holes in globular clusters? And one particular one to look at is the Omega Centauri, because it's the most massive globular cluster. It is to all likelihood, or we can be sure, it's actually not a traditional globular cluster because it was the nucleus of a dwarf galaxy. So, but is there now a black hole or not? And so the problem is that it's not completely trivial, yeah, to do this, or far from trivial. I don't know why it looks so bad, this figure, but what's shown here is in log in radius from the center of the Omega Centauri, the globular cluster, outwards. And what is shown on the y-axis is the velocity dispersion. As we saw before for a map, if there's a black hole, we expect a peak in the velocity dispersion. And then you see two different measurements. You see radial velocities in blue, and you see proper motions from the Hubble Space Telescope in red. And you see already from the two measurements that they disagree. Yes, so one says the radial velocities, there is a peak, so there is a black hole, and the proper motions in the same galaxy, yeah, the same globular cluster here, says there is no black hole. Yes, and this actually has been going on for not only Omega Centauri the last 10 years, but for many other globular clusters. Data and studies shown black hole, other studies shown there's no black hole. Yes, and so one of the problems obviously here is that these are bint data, while for these nearby globular clusters, we actually have individual measurements. And if you start binning your data, then you lose information and you get biases. Yes, so that's one thing that you should not do. But okay, fine, you shouldn't do binning, then give me a modeling technique where I can do this star by star. So that turns out to be rather challenging. Yes. So, and you see in prep still there because we did this with Laura Watkins. And then we found a black hole there, like 10 to the 4, so 10,000 solar mass. But the problem was that we were not convinced ourselves whether this was really a proof that there was a black hole. For the simple reason is that we then asked the question, because we fitted star by star, which stars are then moving faster? Yes, because if there's a black hole and you prove it, then you would also expect that there would be fast moving stars around it. And we didn't find them. Yes, we could not convincingly identify them. And there are all kind of other issues. Yes. Yeah, you have to deal with mass aggregation, with stochasticity, etc., etc. Yes, so it's not completely trivial. So then we set out and asked ourselves, actually, a really excellent PhD student, can we, for Omega Centauri, there's such a fantastic data set, can we actually find directly fast-moving stars? Yes, and the answer finally is, so this is again, sorry, yes, this is a slide from a postdoc here who collected like from the literature, black hole, no black hole, black hole, no black hole. Yes, so you can make a really nice overview, and for every claimed black hole IMBH measurement in a global cluster, there's an equal amount or more papers that say the opposite. There's no black hole. So, and then this should be playing. Let me see if it works. Even music, sorry. So this is what the PhD students did. So this is really Omega Sen. He went to the archive, HST archive for the last 20 years, got all the data that is there in Omega Sen, and remeasured proper motions for 1 million stars. And then it's really looking for a needle in a haystack. Like, are there, among these 1 million stars, are there stars which move faster than they should? Yes, and should is, if there would be no black hole, yes, then these stars that you see here appearing are moving so fast that they should have already left the globular cluster. Yes, so the only way they are there is if there's if there's a central mass concentration. Because we don't see its central mass concentration, it has to be a black hole. And so how does this then look like? So here is, for example, a figure on the left. So this is for one star. You see the amount of observation epoch on years. Yes, so it is over 20 years. And the reason there's so much data is that because Omega Sen is a calibration object for the Hubble Space Telescope. So every few months, the Hubble Space Telescope goes to Omega Sen, takes a picture for calibration, which is great for us because then there's tons of data. And so what you see here on the left is for the single star is the change in RA in milliarc seconds and in declination in milliarc seconds. Yes, and on the right, I think this is always very illustrative. So this is a fast-moving star. You see over 20 years, it moves almost 1.5 pixel on the HST. Yes, so you can, the HST is so well calibrated and so stable that you can actually measure movements of hundreds of an HST pixel. Yeah, so this is, I think it's really, really impressive to realize that we have such an instrument. But here you can really see for these fast-moving stars over the years, it's actually moving with respect to the stars around, which are more or less standing still. And so if you do that, then you find on the left are all these fast-moving stars. Yes. So for some of them, we also have the line of sight, not only proper motion line of sight. So we have even the 3D motion. And then you see all these purple, and then you see immediately there's a bunch of stars in the center. Yes. And these are really moving fast. And if these would be foreground stars, for example, that's excluded, because you would only expect half of foreground stars there. So these have to be in Omega Sen. They're all clustered there together, these 7. So the only solution that is left that is there's really a massive concentration. And because the area is so small and we don't see anything else, the only viable leftover solution is that it's actually a black hole. And just to illustrate, so this is, I think, the diagram that's really showcase it. So you see the radius from the center outwards, and then the flat line is the escape speed. So if there would be no black hole, because the core of Omega Sen is, the density is flat, the escape speed is actually constant. Yes, so around 62 kilometers per second. And then some error bar. Yes, and then in purple, you see the stars that have been measured their speed. Yes, and you see that that all of them are above the escape speed, but at especially those 3 stars that are well above the escape speed. Yes, they have lower limits, because for those we only have the proper motion. So we're trying to get the 3D motions. But of course, the proper motion gives you a lower limit. And so with that lower limit, you see that you need to add a point mass and a center. And this is exactly that curve that you see there is with a point mass and IMBH of 8,200 solar masses. So with this lower limit, it has to be at least 8,000 solar mass black hole. And a most likely estimate based on models and on n-body models and dynamical modeling is actually that it's a 40,000 solar mass IMBH. But we don't have the proof for that yet, because we need the 3D motions of the stars. So also looking, yes. So, and then the last part to wrap up things is what if we now combine the two together? So the power of the stellar populations and this of the dynamics, what can we then learn about the past of the galaxies? And so in principle, what we're after here, when we started this was, you all heard about the Milky Way and the Gaia Enceladus sausage, or the sausage Gaia Enceladus, or whatever. This detected merger like from 10 gigayears ago. And probably you have also seen or heard about that this like streams in Andromeda, that they represent a merger that happened 2 gig years ago, but that was very massive. So now the question is, this is all done with resolved stars nearby. Can we also do this now, like for galaxies for which we cannot resolve the different stars? Yes, and I'll hope to convince you the answer is yes. So how do we do that? So we again have the same orbit-based model as you saw before. So this is the same galaxy with the same model, with the same plot as we saw before, but now we have like taken out this inner halo, because these stars are on radial orbits, yes, but they on average spend most of their time outside of the center, yes. And as you know, stars have to be born in a disk, yes. So there's only one solution that these stars came there, is they were born in a disk. So they were born at, let's say, higher in this plot around 1, but then they were either accreted from externally, because then they could be in radial orbits, or they were heated in the sense that they went from disk-like orbits, they were kicked up and became radial orbits. If you then go to the simulations, then actually it turns out to be, if you measure these, if you find these stars and you measure their mass, which we can do very robustly here, then it turns out to be that this is irrespective of which simulation you look at. Yes, so there's equal T and G here, that this halo mass, which is shown on the bottom, is actually 1-to-1 correlated with the most massive ancient merger. Yes, so the most massive past merger. This X1, Xito1 means the most massive accreted system. And so what you can do now, yes, and all these massive galaxies, they all show such a let's say major merger, or massive past merger. And now you see in red, yes, so we can measure this mass, halo mass, and we can then read off what was the mass of the past major merger. Yeah, so we have at least an idea of the mass, but what about the timing? So when did this merger happen? Because in the light distribution, it's completely smooth, so it must have happened a long time ago, but what is long time ago? And so for that, we actually do now a next step, what we've done in this orbit-based model. And what we do is we not only fit the motions, but we also color the orbit. So we say every orbit, we calculate, we also assign a stellar metallicity and a stellar age. And this means that we can then also fit the maps of stellar age and metallicity that's shown here at the top. And that indeed we can get a very, very good fit. And this actually converges very nicely. So now, in addition to the motions of the orbits, internal motions, we also have what age and what metallicity these stars are on. And then you can do something really nice with it. And that's shown first here for the simulation. So you see a simulated galaxy to the left, an image. Yes, there's a lenticular galaxy. And this lenticular galaxy had a major merger. Yes, and this major merger, now what's plotted on the x-axis is at age, so the left panel. So 0 means now, and then going back in time, yes, up to the age of the universe. And then what is on the y-axis is this circularity. And so what you see is that if you go to young ages, yes, up to 7 gig years, there are only cold orbits. Yes, so this means stars that are born in a disk and stayed in the disk. Yes, this immediately means that nothing dramatic happened to this galaxy the last 7 gig years. No major merger, because if there would be a major merger, what would happen is that exactly what you see for the other stars, they all were born on thin disks. Yes, so they were all born at 1 or -1, but then they were because of the merger, they were all scattered, yes, to radial orbits. So that's why there's this blob at 0. That is because of the major merger scattering the stars everywhere. Yes, and so this change from like stars scattered, like with all type of radial orbits, to purely be on cold orbits. That really identifies the end of the merger. Why does this? The merger is happening, stars get scattered, there's gas left. Once the merger is over, the gas settles and stars forms in this disk. Yes, and that is what you see here. Of course, this is directly from the simulation, so you can perfectly make a very smooth, nice plot. But what we did now is we simulated IFU data from this. We did a Schwarzschild model, we colored the orbits, and then you get the plot here, plot B. This is what you infer then from the Schwarzschild model. Yes, so this is really all the orbits that you fit with the orbit weights. And then on the bottom axis, you set the age. So you see, of course, it looks worse than on the left plot. Why? Mainly because getting ages of stars is very difficult, especially old ages. But you still see this change. Yes, so this transition. And if you go to the real galaxy now, this galaxy that we have seen, you see a very similar pattern. Yes, so you see that up to 10 gig years ago, yes, there's only nice disk-like orbits. And if you go beyond 10 gig years long ago, then suddenly they scatter. Yes, and this is a clear identification that a major merger happened. So now we know from this relation the mass. Yes, and from this relation we know when it happened. So this means that we can put in this diagram actually, yes, there was this big galaxy, NG 1380. It had a merger about 10 billion years ago. Yeah, so this is an illustration that where we want to go is that we can, for single galaxies, find out what was their past in major mergers, as well as I showed in the beginning, that we can handle on the satellite. So the goal is really to rebuild the history of the galaxies. And for people that are interested, what I show here is similar kind of plots have been used for the Milky Way to identify this Gaia Enceladus sausage. Yeah? So this kind of technique is very, very much along the lines of what's done with the resolved stars. But resolved stars we can only do for a handful of very nearby galaxies, while the technique that we developed should be applicable to many hundreds to thousands galaxies. Good. There's a review that we're finishing. And then what I wanted to highlight here, this is what we call extragalactic archaeology. So the only big but is, so you would ask, why haven't we done this for 100 galaxies then? Because it's super time consuming. Yes, so the data is huge that you have to deal with. The models are expensive. And then you have to combine the two. And that means we have to go to a kind of machine learning, or what we're doing now, team up with very smart mathematicians, yes, that help us in developing techniques to speed this up. But I hope I convince you that the technique is there. We have a few cases already, showcases, where we really, I think, clearly show that this is possible. And the next step would be to further develop, and especially to speed this up. With the major goal, again, where we started with, is to rebuild individual galaxies their past, so that we can really trace back for multiple galaxies what happened in their past. And this, of course, is not done on my own. This is with a whole group here, and with pictures shown here. And then I wanted to point out that on the bottom, there is this dynamite code. So this is the dynamical modeling code. So we do really an effort also with a software engineer to make this publicly available, of course, in step by step. So what is available now publicly is this code, which can do the kinematic fitting, including a bar, if you like, black hole measurement, etc. But the coloring of orbits is not yet publicly available. That's what we're doing in the next half year. Yeah, so if people are interested, you can go to the website, you can download it. I heard today, actually, no, yesterday, from two people completely from a different group who managed to able to download and get it installed and working. Of course, it's not a black box. Yes, so for people that are really interested, we like every year or year and a half, we also organize workshops. yes, dynamite workshops, and if people are interested, then we will have a call and people can join. Yes, so hopefully we aim to have the next one in like mid of next year. And that was, I think, yes. Sorry, I will go back to the play mode. Good, that was it from my side. Thank you.
Thank you very much, Glenn. Do we have questions from the audience? Basilio, do you want to come over?
Thank you very much for the talk. I was wondering about the intermediate mass black hole in the center of Omega Sen. The center of globular clusters are environments where two-body stellar interactions occur very often. For instance, a three-body problem like a binary star and a third star, the binary may donate a lot of orbital energy to this third star, and it will acquire over a velocity above the escape velocity. So did you account for that? That student who measured these large proper motions, I couldn't see what the velocities were, but were these interactions taken into account when estimating this intermediate mass black hole?
Excellent question. So we can resolve all these binaries. Yes. So if there were binaries, then we would see them. Yes. So, and these are isolated single stars. Yes.
But if they are binaries with the net degenerate primaries like neutron stars, which may also be perhaps common in old populations.
Yes. So first of all, okay, let me. So I think that we have to. So now I have to go to be a bit careful because I will check it, but I think with the 20-year plus baseline, if it would be a neutron star binary, then probably we could detect from following it motion, we could probably exclude that. So the other point is these are all main sequence stars, lower main sequence stars. So I'm just thinking about what is the chance of that as a binary with the neutron star surviving. And third is that Omega Sen, the binary fraction actually has been measured quite well, and it is very low. Yes, it's like below 5%. So the chance, I think, that all of these 7 are in binaries, and especially in binaries then with compact objects, I think that probably is going to be negligible, but I'm not sure. I don't think we did exactly that calculation in the paper.
Okay, well, thanks.
Hi, Glenn.
Hi.
Thank you very much for your presentation. My question is, to determine the presence of a black hole, which is the resolution you need, with your models? Because you can model the dynamics, and then you can see if you have an increase in velocity dispersion in the center. And but I guess this depends on the distance of the galaxy and the resolution of the observations. But I wonder which is the power of your models, how far you can go from the black hole and still detect its presence with the modeling of the orbits.
Yes. So typical answer is that your kinematics, you need at least some kinematics which are not necessarily the resolution of the sphere of influence, but if you get kinematics that is spatial resolution is not better than twice the sphere of influence, it gets very challenging. Yes. And of course, there have been claims of black hole measurements, but I would be very careful I would at least increase the error bar significantly, because it's not just, so from the modeling technique, it's not a problem. Yes, we can just add more orbits very finely in the center. yes. So from the modeling technique, it just means more computational time, but we can very happily add more orbits in the center. So it's really in the data that you have. And the second part from the data is not only the kinematics. So for example, for this galaxy that I showed, yes, the symphony AO is really critical, because the symphony AO, because it's a relatively low mass galaxy, yes, really makes this peak very clear that it's in the very center. Yeah, so you really resolve it. But the other part is what I also try to highlight here is that, yes, you can still claim that you can measure a black hole even if you don't resolve it properly. It's okay, but you have to typically do that under the strong assumption of your stellar mass to light ratio. And there, I think if you have people there doing stellar population modeling, they will all tell you we cannot do that precise enough. Yeah, so you need to leave freedom from the stellar population modeling uncertainty side and the data, of course, in the mass to light ratio. And you immediately see if you allow the stellar mass to light ratio to vary, you will change your black hole mass. Yeah, so of course, the better you resolve it, the less important the stellar mass to light ratio effect. But this will always be an issue. So far, I think, and it's all about the error bars that you claim or upper limits. Yes, so like if you want an advice for the black hole measurements that have been done so far in the literature, aside of course from the Event Horizon telescope where you really get the image of the shadow, yes, the stellar kinematics is typically the more robust technique, unless you have really a CO nicely rotating gas. But the error bars that are quoted or shown in the papers are typically underestimated. Yes, at least by a factor 2, I would say. That's we can probably safely say.
I have just another doubt. This galaxy that you just showed, it has this the couple rotation in the center. Okay.
Yep.
So when you see that, you still can attribute this to a compact population of dwarf stars. You said that one possibility is this a compact population of dwarf stars, right?
Yep.
Do you think you can explain this kind of observation with compact stars also? Stars?
So this peak in the velocity dispersion and the higher order moment are far too strong to just explain by stars. You need a very compact, such a compact component that it can only be a black hole.
Okay. Well, thank you very much.
You're welcome.
Rogério? Any more questions?
Hello, so thanks for the very nice talk. My question is also related with this supermassive black hole masses determination. So you just said that the symphony data play a very important role in doing that. So, but symphony data are K-band data, so most likely, then you are using the CO bands to fit the kinematics.
Yes.
This is somehow affected by the giant stars.
Yes.
So are you not fitting more the kinematics of like disk-like or something like this? And how could you use this for the next slide, like this ratio between the IMF to play and to somehow decide what is better in the next plot? And besides that, have you checked the value you have found here with some traditional scaling relation like M sigma or something like this for this galaxy?
So yes, it falls on the M sigma relation. It's not a problem, but the M sigma relation, the intrinsic scatter is so large that the factor 2 is easily captured. Yes, so that's not, I think, a very helpful constraint. So on the we are of course worried about that the Muse is optical and Symphony is near infrared. But both are kinematic tracers, yes. So the nice thing about kinematics is that you need a tracer, and it doesn't matter what kind of tracer, yeah, as long as you have good kinematics for it. And in the population, in the modeling that we do, yes, so it actually fits simultaneously the optical side and the near infrared side, yeah. So and the IMF, so this is not coloring. What we do here is that we use the IMF to predict the stellar mass to light ratio, the mass distribution, yes. So one further step here, actually, with the master student, what's doing is literally putting colors on the stars, on the orbits, and then indeed you would expect that for the symphony, that these are clearly completely dominated by the giant stars, while optical, it will still be in light dominated by the giant stars, but there should be more and more contribution from the low mass stars. So, but for the pure black hole measurement, because it's a mass measurement, the coloring is not relevant. Yes, this is really in the mass. So the key point is that we predict, we have priors on the stellar mass to light ratio.
Perfect. Thank you.
I have one more question from Thiago.
Okay, thanks for the talk. Following Rogério's question about the supermassive black hole mass measurements, have you checked it with some other techniques like the genes and isotropic imaging models about the black hole masses? How do they compare to each other? Something like that?
So as you can see here, yes, genes models won't work. You need triaxial models for this, and so far the only workable genes model axisymmetric, and they don't work, you see, in the middle velocity field. Yes, so you have rotation along the long axis and the short axis, so this is hopeless to try to do this with genes models. I mean, you can do it, you will find a measurement, but you should not trust it. Yes, because it cannot capture this triaxial motion. That's the answer for this galaxy. Yes, of course, luckily there are several other galaxies for which the kinematics at least is consistent with axisymmetry, and then indeed it's typically that the genes models give very consistent answers with the Schwarzschild models. Yes, but you have to be careful, very careful, with the genes models, because you have to assume an ad hoc anisotropy. So purely isotropic genes models, spherical isotropic genes models will give you a biased result on the supermassive black hole measurement. So you have to be...
If she sees 1380, for example, it would be okay.
1380, which one is that? Sorry.
The one that you
The
most
one
talked
that you
about.
showed.
The
1380. So...
Sorry for my English.
No. So there, I think we have not done a black hole measurement because I don't think for that one we have actually symphony data. Yes. So for the Fornax galaxies, we only have symphony data. Actually, Maria Lubanova. So I think she has symphony data for 12 or so galaxies, and I'm pretty sure that 1318 is not one of them.
Thanks.
You're welcome.
I have a question now, not about black holes.
Good.
So we've been using the orbit superposition models to get the true relic galaxies, the ones that do not have any significant mergers. And then it's hard to disentangle. I would like to hear your opinion on how to disentangle in those plots that we've been doing with Link. With our PhD student here, Michele. How do we disentangle the ones that have been stripped?
Yes, so
compact and stripped and not real relics.
Yeah, so this is, for example, absolutely not a relic galaxy because it has these inner halo hot orbits. Yes, I mean, because like of course, next the question is, let's take this galaxy, yes, and we would strip it. Yes, what would happen? Yes, so the first orbits that you would strip would be these hot orbits. Yes, so and the relic galaxy should not have these hot orbits, but then is the problem indeed as you described. Yes, so imagine now that it's empty where it's written hot orbits is in a halo. Does that mean the emptiness? Does it mean it's a relic galaxy, or does it mean is it stripped? Are these orbits taken away? So I think there it's hard, but I think with Ling already, yes, that you can do a more statistical quantification in the sense that if it's relic galaxies, that inner area, so where it's warmer and inner halo orbits, there should be completely no orbits there. Yes, so it should be really, really empty. The moment that you get stripped galaxies, what we would have to do simulations, like it would be really hard to completely empty that region, yes, without also affecting the cold orbits and at a certain point also the bulge. Yes, so I think that is and of course if you can tag like if you can tag them with stellar population properties, then the relic orbits should be all old stars. Yes, they should be really, really old stars. They can have, of course, quite metal enriched. Yes, because if they form very quickly. Yes, so if there would be a significant change in age, yes, then of course you would be very suspicious and not call it a relic galaxy. So, but happy, I think with Ling, like you are already following this up, yeah. So, but really happy to learn and discuss more about that. But yeah, the key will be it should be an empty region. But then the question is, if it's an empty region, is it empty because it's really relic, or is it empty because it got stripped? Yes.
Any more questions? I think we have one from our Google Doc. So it's about black holes. And what kind of dynamical modeling is it necessary and required to estimate the black hole mass of Omega Centauri?
Oh, yes. So now we have found these fast-moving stars, but that's not a dynamical model. Yes, that is finding fast-moving stars, and then with this escape speed, you get a lower estimate now. Yes, so if we can measure acceleration of these stars, and it's maybe not completely crazy, because acceleration means in this top left diagram that you're able not to fit a straight line, but also the curvature, because the curvature, the second order, will be the acceleration. Then immediately you have a direct measurement of the black hole mass. Yes, if you know the acceleration, you know the black hole mass. So that would be fantastic. It will be super challenging. And then the question is, how many more systems you can do this is probably extremely limited. Yes. So the other point is, what we will do now is, now we know that there is a black hole. First of all, we will try to get the line of sight velocities, because then we get the orbits around the black hole, like in the Milky Way center. We can then really trace out the orbits. And once we have the orbits, we have a very robust measurement of the black hole mass. And what we will do then, and we already started to do this, is using Omega Sen to calibrate dynamical models. Yeah, so what we want to make is, so what does not work is making a genes model, for example, of Omega Sen. This will not be convincing to get the black hole measurement. So you have to fit star by star. Yes, so you can do this genes with discrete fitting. Yes, we will try that. But most likely you will have to go to this orbit-based model with discrete fitting. And then we can now use really Omega Sen, because it's proven to have a black hole as a test case. Yes, as a validation case. Because if the dynamical model does not find the black hole, then the dynamical model is clearly wrong. Yes, right. That's.
Thank you. Any more questions? You can maybe email Glenn if you have more questions, and let's thank him again.
Thank you.
Thank you very much. A gente tem café. Eu vou buscar uns lanchinhos.
Bye bye.
Bye.
Bye.